In this video, we're going to prove that every regular function on a projective variety is a constant function. So if you're not familiar with some of this terminology, like what is a regular function, there will be some links in the description. But so we have this fact that we're going to use to prove this. The image of a projective variety under a morphism is always a closed set. So that's a pretty difficult thing to prove, but we can use it here. So the first thing that we want to do is we want to note that if phi is a regular function on a projective variety, then phi is a morphism. Okay, so phi being a morphism in this case would basically just mean that, like, if I have if I have a regular function f that's just going from a1 to a1, that if I compose f with phi, that this is still a regular function. And this kind of follows immediately in this case just because we already know that phi is a regular function, and the composition of two regular functions is always regular. Okay, so we know that phi is a morphism. So therefore, by this fact, the image of x under phi, which we'll just call w, so this is contained in A1, and it's closed in A1, okay? And furthermore, not only is it closed, but it's actually irreducible. W is irreducible. So this is something that you can try proving for yourself. But basically, if I have any morphism, it always maps irreducible sets. So X is a variety, so it's irreducible. So every morphism always maps an irreducible algebraic set to another irreducible algebraic set. So W is irreducible. So therefore, there's kind of not that many things that W could be, because we're just in one-dimensional affine space. So it could be A1, right? Or it could just be a point. So irreducible closed sets in A1, the only sets like that are A1 and then just a point. If W is equal to a point, then this just means that phi of x is a point. And then we're done, because that means that phi is constant. So we really just have to rule out that W, so we basically want to show that W isn't equal to A1, right? And then we'll be done. But we can consider, we kind of have the following chain of maps. So we have X. This is mapping by phi to W, which is just A1. And A1 is affine space, and you can always embed affine space in projective space, right? So like if you have an affine point, so I guess like in one-dimensional affine space, if you just have a point like Z in A1, you can think of this in projective space as being like the point Z1, Z comma 1. And so you can kind of identify it this way. And there's multiple ways to identify it, right? Like I can identify Z with Z comma 1, or I can identify it with 1 comma Z, right? And those are both like valid embeddings, right? But either way, there's an embedding which we can call phi 0 that maps A1 into projective space. So then what we know is that phi0 dot phi, this is also a morphism. Okay, and so this also maps x to a closed subset of P1. So phi0 dot phi of x is closed in P1. Okay, but we're assuming for contradiction that W is A1. But so if W is A1, then this basically just gives that that phi naught dot phi of x, this is the same as phi naught of W, is closed in P1. And this is a contradiction because phi naught of W is just the embedding of A1. So this is the embedding of A1 in projective space, and we know that, or you can check that A1 does not embed as a closed subset of P1. Okay, so this shows we know that if W is equal to A1, phi naught of W would be a closed subset of P1. We know that that's not true because we know that the embedding of A1 is not a closed subset of P1. And so this shows that W is just a single point. And that is what we wanted to show. So thank you very much for watching.